welcome to the stage. Jochen is Director of Research R&D at Refinitiv Labs London and Royal Academy of Engineering, visiting professor in data analytics at the University of Sheffield. And from talking with you earlier, I understand you're from Germany, right?
That's right. I'm from an area called Palatinate in the southwest of Germany.
Okay, and it's like there's something funny in the water or something, but there's something unusual about where you come from. What is that?
People don't really drink much water in that area. It's a wine region, although I personally prefer tea, actually. But we have quite a breeding ground for computational linguists, apparently. Does anybody know Martin Volk? Does anybody know Stefan Vogel? Yeah, I see some hands. So all of them are from the same area, pretty much. So where I'm born, actually, Stefan Vogel is about 1-2 miles away from my school. We attended the same sort of high school, and I didn't know him back then, of course. You know, it just happens, and there are some more even. So this is a funny coincidence. Probably no causality involved there.
Correlation always implies something, right?
Yes.
Anyway, so again, thanks very much, Jochen, and we look forward to your talk.
Thanks, Mark, and thanks everybody for having me. So today I would like to talk a little bit about a project that started as a crazy research idea, and as of last September, it became actually a product. So it's called Computer-Supported Risk Identification. I've only got 20 minutes, so basically it's the usual structure, but I will sort of buzz through the various slides, and I would like to thank my collaborators on this topic, which was what we call an innovation idea, not something that was an official project at the beginning, but it started as a coffee chat after I read this wonderful book by Nassim Taleb. Has anybody read the book by any chance? Yeah. So Nassim Taleb, to those who are not familiar with him, was a trader, and he is very smart. So he actually anticipated the 2008 financial crisis and others, and he kind of speculated accordingly. So he became independently wealthy by placing a large number of small bets on very unlikely events. So unlikely that betting on them was cheap, but so impactful if they were to materialize that he could essentially retire. And he has some name for such a strategy that I cannot say here because it's not a very polite language to use. But basically his main notion in this book, the black swan, as the title suggests, is a black swan, which is the threat of a high impact event or risk that may turn into a high impact event where there's a cumulative tail risk involved. And actually a lot of these scarce events that are pretty much unpredictable, taken together, comprise a substantial amount of probability mass. So one of them will eventually happen. And his main dictum in that book, which is the first of a series he wrote, is that you can't ignore that. The world will change, and that change will be driven by that long tail of probability mass, not by the things everybody's talking about. And that's fantastic. So I was immediately, activated as an NLP research person, and I thought, and I talked to my colleague Frank at the time, what can we do not to detect black swans? They are by definition undetectable. That's a defining criterion, but there's a sort of a weaker notion of a gray swan. What can we do to detect gray swans so that there won't be a crisis like what we had at the time, 2008, 2009, when we talked about that? And there's, of course, value in knowing about risk exposure. After all, we are in a building that thrives on modeling risk and benefiting from risk and insuring others for events that they can't carry on their own. So we came up with this idea that we dubbed risk mining, because back then there was actually no method that could help you when you were gathering risks in a so-called risk register. A risk register is essentially a document that contains a set of the risks that an entity is exposed to. And as you can imagine, how people gather their risks, they sit around a boardroom table with an empty spreadsheet. And they say, okay, what are we exposed to? And they list the things that you would expect them to list, because it's the obvious stuff, right? And the problem is, if you haven't got any automated support, you may miss out on things. And we studied a couple of SEC filings. Those are disclosure documents that public companies have to file. And there is a section 6 in the annual so-called 10K filing document where companies have to disclose their risks. And there's all kinds of stuff in there that probably doesn't matter. It's not the real risks that these companies suffer from. It is stuff that they copy and pasted from their competitors' filings to avoid being sued for omitting those risks, and things they could think of easily, and so on. So we thought, what can we do to create a more consistent way to deal with risk identification? So this is not about determining the probability with which a risk turns into a bad event. This is also not about somehow magically calculating some impact of something that might happen. This is really just the first step of identifying what's here in this red box, the set of all the risks that an entity is exposed. If you haven't got that set, or if you have got it but it's incomplete, you can't do risk management well because you can't manage the risk because you haven't identified it. So only if you've identified it can you categorize its likelihood and impact and make mitigation plans, or in fact take insurance. So the research question is, can risk registers actually be extracted automatically? And if you want to extract something, the obvious question is, from what? Now, having access to this fantastic resource that is Reuters News, with its high-quality journalism behind it, this was an obvious choice, right? So using journalists, professionals, whose job it is to dig up all kinds of positive and negative information, it would make sense to use that. And so the goal is to take news text as input and to create a set of company risk registers, sets of risks for each company that they are exposed to. And then to do that, we initially didn't know, okay, how shall we structure that? And then we came up with the idea to break the problem up into two parts. The first part was about creating a taxonomy of all the risks there are. And you may say, oh, well, how does that look like? And we didn't know either. But then if you have such a taxonomy of how things are really called, then you can look them up in text. And you can sort of detect whether somebody is exposed to that risk type by looking at company names, for example, mentioned around mentions of these risk types. So after that, you can extract triples of the type company is exposed to risk type. For example, BP is exposed to oil spill risk. And some people said, oh, are you doing some kind of sentiment analysis? And although it has some similarities sometimes, it actually is something different, because there's really not much subjective about the notion of risk exposure. You will all have to agree, really, that BP is exposed to oil spill risk, right? And this is, of course, one of the more obvious cases for purposes of making an example. So whereas with sentiment, whether people like a hotel or a software product, that's really somewhat more subjective. So we believe it's what we came up with is actually an objective, automatic, repeatable, and consistent methodology for obtaining a risk register. It's important that different people come up with the same risks, right? If that is not given, then there's an element of arbitrariness that is deeply unsatisfactory. So here's the algorithm or method that we came up with. We run a web search query in an automated way for so-called Hearst patterns. You may have heard of Marty Hearst's 1992 paper, where basically she explains that such as, in English, is able to elicit examples of a particular thing. For example, examples for cars. And we used that. We said risks such as asterisk. You can try that out in Google or Bing, your favorite search engine, whichever one it might be. It will give you examples for risk types. And we expanded on the work by Hearst by iterating these patterns. So whatever comes back, we actually fed it back into a pattern. We created, let's say, risks such as gives you financial risk, regulatory risk, and other risks. You get enumerations like that in the resulting web pages or web page search summaries. We extracted them, fed it back into the pattern, and iterated. And that way we grew a taxonomy of risk type names that you see in the middle left. And this is grown from the top node, which is simply the word risks, downwards to the more specific words. So risks, financial risk, bankruptcy. So you can run it over one weekend on a 5-year-old laptop with a bad internet connection, as we did, and actually it works pretty well, and it extracts you about a taxonomy of about 10,000 risk type names. And that's a good starting point, because you can put them in a database. You can do a bit of manual noise correction. It doesn't have to be fully perfect, because it's very easy to edit such a file of 10,000 lines. In 2 hours, you can go through it and eliminate all spurious entries. And that's what we call the risk tagger. It took the database and looks up names like bankruptcy in any input text you care about. Now, we now know about risk terminology. The second thing we need is for company names that might be exposed to that risk type mentioned in our taxonomy leaf notes. For example, Kodak. Does anybody know the Kodak story? So Kodak went bankrupt on January 19th, 2012. This was actually during the runtime of this project. On October the 6th, 2011, so just a few months before, obviously there was some chatter about it in the media by the journalists, and we were pleased that this was identified, Kodak's exposure to bankruptcy risk, which is taken here just as an example. So you can look up the risk term, you can look up company names, you can run a company tagger, and us being at the time Thomson Reuters, now Refinitiv, we obviously used Calais, and you're welcome to use Calais if you have a named entity tagging problem. It's out there, it's free of charge, it's a REST API. And it gives you all the names that it can find of companies, other organizations, person names, and so on. And then you can basically have candidate triples of the form Volkswagen exposed to litigation, Facebook exposed to privacy fines, and all the other triples that we got. And we ran this actually for 50,000 companies, and we got hundreds of thousands of different of these tuples, which was fairly exciting. Once you have that, you want to measure how well it works, and you want to think about what can you do with it. So part one is the semi-supervised risk taxonomy learning. You can read more about this in our ACL demo paper from 2010. So we start with these Hurst patterns, risks such as asterisks, financial risks such as you just iterate, and here are some examples of the kind of tuples that come back. So you can see it's working. I just pick out one. Copyright infringement is a legal risks. And they tend to have an S at the end, so they tend to be mined in the plural form, but you can easily strip that off. So after you have the taxonomy, what you need to do is take the news, run the named entity tagger over the company names, look up candidate risks, and then what we did is we parsed the risks, and we built a classifier that basically modeled the whole subsequent processing as relationship extraction task. So for that, we used the support vector machine classifier with a subset tree kernel. I will not go into the maths for that, although I have a slide about it for time reasons. But suffice it to say, here are the 19 features we used. We used 18 pretty standard features that probably many people could come up with. And the 19th feature is the tree kernel. And it turns out that the first 18 together pretty much achieve a similar performance on their own compared to the tree kernel. So they're kind of 19 and 1 to 18 are sort of competing with each other. And if you add them both together, then you get a little notch up, a slight improvement beyond. So we used a dependency parser, so we analyzed all sentences we processed. And I should say that what we didn't model in this is any kind of coreference, which you might want to add to get higher recall. So all the risks exposed in this presentation are about intrasentential risk, where the company name is mentioned together with the risk term within a sentence. And then the tree kernel is used to basically learn whether a company name and the risk term actually reflect this risk exposure or not. So it's a binary question. You send the question into the classifier, and the classifier comes back well, you could say with a yes or no, but we also converted the result, the distance between the hyperplane into a confidence value, which was really helpful to turn this into a product. In terms of data, we annotated about 4,000 sentences from the Reuters Risk Archive. This is a painful exercise. We were successful in getting a Fleischkappa inter-annotator agreement of about 80%, 0.79, which we found satisfactory, but it took us a couple of rounds to get there. It's really hard work. And we used a binary annotation of, does this example sentence really stand for risk exposure? So based on this sentence, would you agree that there's an expression of X is exposed to Y or not? So pretty simple binary annotation task, but there were subtleties based on the complexity of these examples. We didn't find it particularly easy to do this annotation, but of course, you know this is quite often the case. And then we ran, as a baseline, a simple lookup tagger. So obviously, you could just look up all these risks. Let's say somebody who doesn't know much about machine learning or NLP might just build some kind of list of all the risks as far as they know and look them up, and that's it. So can we do better than such a person? As it turns out, yes, we can, because a simple lookup tagger may get like 65, 66% in F1. Obviously, lookup gets really good recall, but it also creates tons of false positives. And we'll get back to false positives because they are really a problem for banks, and we'll get back to that, who also need to look up things about their customers to comply. So our tag at the time was 82.3% in F1, and the best combination, the best result was delivered by the combination of the tree kernel with these other feature vectors, so all the 19 features together, where the tree kernel was combined in a linear way with the feature vector for all the other features. Now, does this work at all? Beyond the numbers, do you believe this? So we tried something manually to trick our own system. Microsoft are facing a fine, said Bill Gates. So Microsoft is the named entity, the company that may have some exposure. Fine is a regulatory enforcement action, and the SVM says 96% yes, this is risk exposure talked about here. So we tried something else. I feel fine, said Bill Gates at Microsoft. Pretty much similar tokens, right? But the meaning is different. And as you can see, the result is 25.9. And whenever that value is less than 0.5, we are statistically doing better by saying, no, this sentence does not actually express any risk exposure at all. So this gets both right. That's why there are 2 ticks. And this is actually sort of contributing towards solving the so-called false positive problems. So when banks do background checks on people and on companies, when people open bank accounts, and from that point on, again every night in a batch process, to be compliant with so-called know your customer compliance rules that mandate that everybody gets checked a lot of times to make sure that they're not involved in financial fraud or terrorist type activities, then this false positive problem of I feel fine, can cost banks a lot of money. They may have to employ literally thousands of people to solve this, because it has to be done again and again and again, because the world is changing. So very brief discussion. So we have 2 findings here. First of all, the scientific finding is actually effective to use this combination of taxonomy learning plus supervised learning of the mentions of the risk terms and the company names in context. And a tree kernel is an effective means to model risk exposure of mentions of these exposures in news. So that's the scientific bit. The engineering finding is, well, you can either use a tree kernel or a set of these features. Actually, it should say 18 here. So they're both equally effective. If you want the best performance, absolutely, then you should combine them. But you could do one or the other to keep things simple if you want. And at the bottom, I show a bit of an internal demonstrator. This is not a product. This is essentially something that we built to internally show around what we can do. Because research needs to be sold. like a product internally in a large organization. And the best way to do this is essentially building a demo, just like startups build demos to impress external customers. So in some modified form, with some further development, this became part of WorldCheck Media Check since September 2018. It's the solution that Thomson Reuters, now Refinitiv, is selling to the compliance industry, for example, banks. This is a 500 million market. And we got some nice feedback. So the system has been called a financial Robocop by an influential financial blog that we did not pay, as far as I know. So thanks for that. So in summary, we presented the first method for computer-supported risk identification, which prior to this work, as far as we know, was entirely manual. We combined semi-supervised learning to learn a taxonomy of risk types with framing the classification problem as relationship extraction using an SVM with a tree kernel. The resulting F-score of 82% roughly is satisfactory, and the resulting solution after further work has been deployed in a commercially successful product. So in this talk, we addressed only risk identification. As I said, future work should investigate the additional dimensions of the triple risk identification, risk likelihood, and impact of when the risk becomes a reality and materializes, for better or worse. And I think this is the area of combining risk with NLP is a fascinating field. So there's a lot more that you can do. For example, apply this to other languages, combine this with other models, and even use applications that are different from purely regulatory compliance applications, for example, to help investment management. Thank you.
I just need one of the mics. So questions? Alex?
Hi, interesting talk. I'd like to ask you a bit about the error analysis. So, but both qualitative and quantitative. So you referred to the fact that false positives and false negatives are both important. So it would be nice to see the trade-off, like how does your ROC curve look like, or like just some insights into it. And also on the qualitative part, I would expect that since you rely on the parse trees, that might be a big aspect. So if the parse tree is incorrect, then does your model break immediately or not, or is it robust?
Yeah, it's a good point. So last question first. So if the parser gets it wrong, of course that hurts. But it's somewhat caught up by the machine learning process, because that can sometimes learn, which constellations, even given a broken parse tree, result in a yes and a no, because it's supervised learning. So the supervision obviously is helpful, but not always. Obviously, there's a cost of a wrong parse. That's why we're doing this. For example, if the entity that is exposed is not the entity that was supposedly recognized, then it may say no because it thinks, in quotes, it's about another entity, right? Those are cases where the parsing hurts. Now, the other question was about quantitative versus qualitative?
Like the false positive versus false negative.
Yeah,
trade-off.
So it's there. The paper has more detail about that. So I do have a slide, but I guess we're kind of out of time now. But I would suggest consult the paper about it. So there's learning curve, and I think confusion matrix should be in the paper. And I'm happy to share a copy if you can't locate it. But it's the ACL one from 2010 is freely available. The 2016 SVM paper is behind an IEEE paywall, but I think I may have a PDF somewhere if you can't get hold of it.
Thank you.
Thanks.
Thank you. Cesar, behind you.
I just have one question. How did you build up the negative set?
Yeah.
Because there is a lot about positive.
Yes. So you can sample sentences that are potentially confusing. For example, the easiest way is you take random sample. That's not ideal because you want to introduce some confusion with the existing company named entities, right? So we actually looked at the ones that had the same company mentioned in it. And you can go beyond what we did. You can make up various scenarios that are all confusing. For example, use more words that are also in the positive set, but with a minus sign in the annotation. And we were probably not very sophisticated along these lines. We had the idea, but there was not so much time for that. But we did make sure that the named entity is included.
And you didn't try to like this, when you were creating the positive set, that would have already some sample which are probably negatively selected from your algorithm, while extracting risk associated with companies. So maybe risk as a term just pops up in a news article, but it's not a risk paper or risk news article. So you then try to look into that set.
The set of?
So you mentioned that you extract risk
Yes.
with associated companies.
Right.
I believe that not every news article that mentions risk with a company name is actually a risk article.
Correct.
So you didn't try to look into that sample?
No, we did. So we built an indexed version of the news articles, and we looked at the pair, and if they occurred with pluses and minuses, we took all of that in. Okay. And we had to fill up with some extra minuses. It's always good to have more minuses. And a related question is the question of balancing. How many positives and negatives do you need? I guess I'm not technically sort of able to give you a lot of details about the sampling because there was some stuff used that is really confidential.
Okay.
But again, I would refer you to the paper, which has the amount of stuff that we could disclose about the sampling and your question.
Perfect. Thank you.
Thanks.